Welcome everyone to section number 6. This is implicit differentiation, and I'm happy to say we have a relatively short video here for you. I just want to get you introduced to these ideas of what types of problems is implicit differentiation good for. Why do we need this thing? So the claim is, so far everything that we have differentiated, taken the derivative of, has been a function. But there are plenty of curves out there that aren't functions. So I kind of wanted to go through this kind of side-by-side example here. So you can see that this curve right here is a function. Just by looking at it, I can see that it passes this vertical line test. Remember, the vertical line test was this thing to determine, from a graph, is the curve a function or not? Can you solve it y equals something as a function of x? And likewise, over here, you can see fairly quickly that this does not pass the vertical line test, So this is not going to be a function. You can't solve this y equals. When you try, you're going to have a square root, and you're going to have a plus and a minus. And the claim is the positive square root will refer to the top half of the circle, and the negative square root will refer to the bottom half of the circle. So you can't just solve this y equals. You kind of need these two pieces. You need to kind of split it into two. And so looking at these graphs, my first goal is to say, okay, can I figure out, or can I approximate at least, what the slope of the tangent line would be at 1, 1? And so sure, we've done this game before on functions, but I should also be able to do that here even when it's not a function. Notice that I've specified both the x and the y value. If I just specified the x value, you wouldn't know if it was, well, x equals 1 has 2 points, So it's up here, and also down here there's another point on the curve that has the x value 1. So, but when you specify both the x and the y value, well, then you kind of are talking about one specific point, and again, you should be able to approximate the slope of the tangent line, aka find the derivative. So let's go through this fairly quickly. Let's start with the one here on the left. So I would like to approximate the slope of the tangent line. So I'm going to go ahead and try to sketch my best tangent line. So something like this seems pretty decent. Okay, and I want to do a rise over run situation, because I want to figure out the slope of this thing. So, okay, let's say I notice here that if I go over 3, I seem to go up exactly 2. At least in my sketch, Yours may be different. This is an approximation, So here the rise would be 2, the run would be 3. So I'm going to go ahead and say that the approximate slope of this tangent line, aka the derivative here at 1, 1, is going to be 2/3. So I'm just going to say m equals 2/3. That would be, approximately the slope of the tangent line. Okay, now over here, still we have the graph, and I'd like to approximate the slope of the tangent line, again at 1, 1. So let me go ahead and sketch maybe my best tangent line approximation, something like this maybe. A nice straight line contains that point, just barely skims the graph. Alright, and so actually this one I noticed that if I go over 1, I seem to go down exactly 1. And likewise, if I go over 2, I seem to go down exactly 2. So, okay, in this case, the rise would be maybe -2 for a run of 2. So therefore, the rise over run would be -2 over 2, which we could simplify down to just -1. And yeah, this does seem to have a slope of -1, For each kind of x that I move over, I seem to go down 1. So, okay. That's my, again, approximate slope of the tangent line, or my approximate derivative. Now let's go fairly quickly, So through this one, because this is just review right here. Now we're going to use calculus to find the slope of the tangent line for this function here at 1, 1. And in this case, go ahead, pause your video, and I'd like you to solve this problem for me, So take 30 seconds, solve it as far as you can. Again, pause the video, and then I'll spoil the surprise. All right, and here we go. And see, I went ahead and rewrote this, Everywhere I saw this 0.5, I changed this to a 1/2. So I haven't taken the derivative yet in this line, just because, when you do take the derivative, this 3 comes down, and I wanted to write this as -3/2, It's easy to kind of make these fractions talk to each other and manipulate these fractions. Here, when you multiply 3 by 0.5, you just need to know that that's 1.5, All right, likewise plus x plus 1. Then we go ahead and plug in the x value 1. Notice there are no y's or anything like this, so this is kind of some extra information here. So we get y prime of 1 is equal to 0.5. So our approximation was off by a little bit, right? This is around like 0.66. This is 0.5. So yeah, it was approximation. So the actual answer, right, 0.5 or 1/2. Okay, let's try to do the same thing over here, approximating the slope of the tangent line through this nice circle, x squared plus y squared equals 2. So the idea here is that we're going to take the derivative on both sides of this equation. Kind of like when we're over here, technically I take the derivative on both sides, right? Because the derivative of y is just y prime. And then the derivative of the right-hand side, well, is all of this. So really, we're taking the derivative on both sides. So let's do this kind of with our implicit differentiation problem over here. So if I was to take the derivative on both sides, and I guess I'll start off in red here because I'm going to do this wrong. But this is a common mistake that I see, so I want to kind of bring it up and talk about why it doesn't work. So if I was to just take the derivative on both sides, maybe a first guess would be 2x plus 2y is equal to 0. Right? So I take the derivative of x squared, I get 2x. I take the derivative of y squared, I get 2y. And I take the derivative of 2, and the derivative of a constant is just 0. And now let's back up and remember what our goal was, right? Just like over here, we wanted to solve what is the derivative? What is this y prime? Well, over here you can notice that I don't have any y primes. So that's going to make us really hard to solve for slope, right? So I got to wonder, like, what did I do? There's no y primes here. How can I solve for the slope? And so it comes down to, we forgot the chain rule, right? We forgot we're taking actually the derivative with respect to x, and we need to think about the chain rule. So again, this is wrong. And let me kind of talk through then what the correct way to go about this is. So again, we're taking a derivative with respect to x. So when you take the derivative of x squared, you get 2x, right? Because this is really 2x to the first power. But if you'd like to, for just a second now, I'd like to think about, well, there's technically this inside, right? The inside is x. And so when you take the derivative of x, you get 1. And so this is just multiplying by 1, and so it doesn't usually come up. However, the new thing here, when you have this y, well, the chain rule is now very important, right? Because when you take the derivative, you get 2y to the first power. But then when you take the derivative of the inside, right, the derivative of y is y prime, right? Maybe I really need to emphasize these are 1s right here. And that is a y prime. Again, the derivative of y is y prime, or dy dx, right? There's a couple different ways we can denote this, but when I took the derivative of y over here, right, I got y prime, the derivative of y. So it's the same thing over here. When I take the derivative here, and now I have something more complicated than just y, right? So I have to apply the chain rule. The 2 comes down, I get y raised to the first power, then I multiply by the derivative of the inside. And so the derivative of the inside is y prime. Now I set this equal to 0, because again, the derivative of 2, constant, it is 0. And now the claim is I'm set up for success. So let's go ahead, maybe I'll take one line to simplify this. I'm going to write 2x plus 2y, y prime, is equal to 0. Subtract 2x from both sides. 2y times y prime is equal to negative 2x. And again, remember my goal here. My goal is to solve for the slope of the tangent line. So I'm going to go ahead and solve for y prime. So let me divide by 2y on both sides. So this is going to give me y prime is equal to negative 2x over 2y. And now you can see that the derivative depends on both x and y. Because, remember, if it only depended on x, you couldn't tell kind of between these 2 points, right? The blue one and the red one. So you have to specify exactly which point you're talking about, right? What is the x value and what is the y value? So in this case, we know our x value is 1 and our y value is 1. So therefore, we're going to have the derivative at 1, 1 is equal to, well, negative 2 times 1 over 2 times 1. And so we get negative 1. And this is exactly what we approximated it out to be up here. So actually we did a pretty good job on this one. All right, so that is the process. I just have one more little definition here on this next page before we take a break, right? So implicit differentiation, when we say these words, this is the method of differentiating both sides of an equation with respect to x, and then solving the resulting equation for the derivative of y, right? Y prime. Also, I want you to remember that this is, sometimes we use the Leibniz notation, and this is dy dx. So this may, show up in your homework or quizzes or exams. So again, y prime is just another notation for dy dx. It's a derivative of y with respect to x. All right, so that is a good introduction. Next time we're going to be doing lots of examples, right? We're going to apply this to a lot of things. We're going to get some more practice. I'll see you then.